Okay.
Hi, Tomasz.
Hello, hello, everybody. My PhD student's wife is giving a birth now, so yeah, I'm not sure the final results because I found this information about an hour ago. So I'm a little surprised. So I'm not a perfect ready, but I must present our common presentation. So I think that I could do this. So thank you very much once again. And this presentation is with my co-authors, my colleagues, my PhD student Robert from also Adam Mickiewicz University, because I'm from Adam Mickiewicz University in Poznań, Poland. And Robert also is from this university. He's my PhD student, and he also works for OLX group in Poznań. And we used data. This is for this presentation. And our third co-author is Agata from Poznań University of Economics and Business. She also works for OLX group. Okay, so simple outline of my presentation. At the beginning, I present the idea of graph models. Next, I present our approach. In the third point, I will present how we trained the model, and finally I show the results and some summary. Okay, so for recommendation, we have, of course, users and items. For each user, we would like to find some good items to recommend. And in such situation, we may present our data as a bipartite graph, where each user and item is represented by a node. On the right, you can find very simple presentation of this idea. And the edge between nodes exists if there was an interaction between a user and item. It's very, very simple idea. And to find recommendation, we have many approaches. For example, producing no embeddings, not to vec, deep walk, light GCN, and some direct score calculation. For example, P3 alpha and RP3 beta. And our approach use direct score calculation. So we try to calculate direct scores. And in classical approach, like RP3 beta model, the score for each node is calculated as the sum of scores assigned to the path of length tree, connected user and item. And here we have the very simple formula where the nx is the set of neighbors of the node x, and we have two real parameters. Maybe better is to say that they are hyperparameters, because we must set them before training process, but here we don't have even training process. We can calculate directly the scores. Okay, and the score, as I said, is calculated as sum, and we have some advantages and disadvantages of this model. Of course, it's very popular. This is, of course, the great advantage. And we can find information that this model is very useful and has great performance on several data sets. It's very simple. This is very simple. As you see, the formula is very simple. Interpretability, we have good interpretability of this model. Efficiency is fast. And some advantage and disadvantage is that we don't have the learning process. Of course, because we don't have this learning process, it's fast, but it's hard to tune this model. It's rather not possible to tune in easy way because we have only two hyperparameters. And in such model, it's hard to include additional features, because sometimes we have some additional features for users, items, and we would like to add such features to our model. It's not easy to add, maybe even hard to add. And Because of this, we try to propose new model in which we will have parameters which will be trained during the train phase. Okay, so what now? Of course, we take the idea from the RP3 beta model, and we calculate the score as before, but now for each edge, we have different parameters here, because it's a sum like area, where P, X, Y, K is the score assigned to the edge connected nodes, X and Y. For each layer, we have 3 layers. As I said earlier, we have 3 layers because we are looking for path of length 3. Okay, so now how to calculate these scores? Because this should be the function of the node features and edge features. So it will be much easier to add additional features. And this is the very looking simple formula where we have that the score is calculated as some function called feature encoder here. And we have feature vectors of nodes, feature vector of edge, and some real function. This encoder is real function. This could be, for example, neural network. And of course, the choice of these feature encoders depends on dataset. In our dataset, because our dataset is a clickstream data consisting of tuples, we have user, item, event type, timestamp. So which each pair may appear several times. So in this situation, it's very useful for us. We have additional information, additional features, for example, timestamp and event type. Okay, so here our proposition of feature encoder. Let capital E will be the set of all possible types of interactions, because we can have different types of interactions. And now we define the following features. Degree of node, simple. Rec, the number of days that passed between the most recent user interaction with the item and the most recent interaction of this user with any item. The number of interactions of the selected type between X and Y, and number of interaction between X and Y. And now how we calculate the score. Here we see the formula. So we take degree, we have some parameters for here, dk, rk, ek, b, e, and b are parameters that are tuned during the training part of our method. So we're taking degree is very important here, simple idea. And here is the idea similar to logistic regression. Some part we have for each layer, for each K, we have different, we could have different values of parameters. This model is definitely learnable. And the basic model which we use as a baseline, RP3 beta, is not learnable and has only 2 hyperparameters, as I said, alpha and beta. And of course, because our model is more general, and for some values of parameters, our model is equivalent to the RP3 beta. And when D1 and D2 are equal to alpha and D3 beta, and all other parameters are fixed at to 0, our model is equivalent to RP3 beta. Of course, this is also, we can find some set of parameters for each our model is equivalent to P3 alpha, and of course 3 paths, because our some special cases. So naturally, our model includes these models. Okay, so now how to train? How to train our models? We need loss function, of course. And here, this is an algorithm how to train iteration. We iterate over some number of iteration, and we update edge weights of the graph based on feature encoders. We set the loss to 0 for each batch. We pick a random user and take his most interacted item as a validation node, and we make forward pass for this user and calculate the scores. And next, we backpropagate the loss, like in neural networks. Okay, what is important, as I said, also is a loss function. The idea of our loss function is to score the validation item higher than any other items. And we define some kind of like what we call ratio. This is average score of top k items divided by validation node score. Additionally, to stabilize the training, we calculate the sum of squares of the parameters and multiply it by a constant regularization parameter. This is common technique to regularize to prevent overfit. And we consider three loss functions. The simple ratio, so ratio plus regularization term, log ratio, logarit of ratio plus regularization term, and some boosted log ratio, so logarit of ratio, some validation node position, and regularization term. And now a little about results. Of course, we should find model parameters. We use Bayesian optimization using Gaussian processes, 100 iteration for each model, and we optimize it precision at 10. And from this box plot, we can observe that what is important, in my opinion, what is very important, that our method is very stable, and for it is possible to find good hyperparameters. And for each run, we obtained parameters which are rather good. And for RP3 beta, we must be very careful, because before learning, we must set hyperparameters. So when the hyperparameters are bad, we could obtain very bad results. Of course, we also compared our method with methods which are less general, they're RP3 beta. And here we have table with accuracy results. We can observe for that our data set. We have, in case of our data set, which is connected with OLX jobs, our model is better for each measure which we used. What is also important for recommendation, it's important to recommend not only the same items for every user, but recommend a lot of different items. So we calculated coverage, and the simplest to interpret, of course, is the test coverage. This is the percent, the fraction of items from the test set which were recommended to at least one user. So we can observe that our method recommended over 75% of items from test set, and it's much better than other method which we compared. Also, what is quite interesting, what about overlapping of methods? Because maybe methods are very similar and recommend exactly the same items. It's not true in the case of our method, because overlap is for the most similar in ideas, for the most similar method is about 70%. So 30% of items is recommendations completely different. And finally, a few words about interpretation, because we could find some interpretation. Positive values of D parameters mean to mitigate the popularity bias. So we try to mitigate the popularity. So not only the most popular, the best maybe, but try to mitigate this. We have different value, what is important, because for RP3 beta, we will have exactly the same values. And positive values of R parameter means that the more recent interaction have higher importance. It's quite natural that the newer interaction should be more important. And summarizing, we proposed new model. We generalized the well-performing RP3 beta model, and we verified that our model is superior on this dataset from OLX jobs. And in the next steps, we would like to explore maybe more advanced feature encoders, and we try to start this on production to measure the model effectiveness on real users. And I hope that that's all few most important references. And thank you for your attention and maybe some questions, remarks. Thank you.
Thank you, Tomasz, for the presentation. And for all the participants, it's time to think about if there's something interesting in the presentation, if you can ask any questions. You can raise hand if you don't have right to voice, and you can write the questions. Tomasz, so maybe one question from me to warm up the crowd. You showed us the graph-based recommendation that is based on this collaboration by graph. I wonder how this approach deals with new users or new items. So if something new appears, yes, the cold start in this graph, because it seems to be quite prone before you have a number of clicks. So how do you deal with such situation?
I'm not sure, because I didn't implement this method, but I think that should be random interaction from the most popular items. But I should ask Robert, because this is some problem. He implemented everything. So I gave only some ideas how to do this, but I think it's in most systems. It's one of the most hard problems in recommendation, how to solve the cold start. Yeah, so I think that's some random items from the most popular items.
Because I also maybe such a hint or such a thought from me. So when I think about kind of a cold start in the graph, when we see, for example, new clicks in jobs in the case of your data, the question is how would the sensitivity look like? So the more clicks, I assume you can fit this isomorphism between those nodes better and recommend better with this model. The question is how this curve is looking. If there is a certain number of clicks, then you can be quite certain about the result.
Yeah, we didn't test this now, but it's a good question. It's very, very interesting idea. So we made similar work for our earlier papers, but now we must add some information about this, how this graph changed when we increase the number of interactions. Definitely.
Hello, Fred.
So congratulations, Tomasz, for your presentation. It's quite clear and very interesting. So I have a question regarding the utility function you have used in your experiment, and if you change it, and how this would impact in your result.
Yeah, as I said, this is our feature direction of work, to change this utility function, because we examined few utility functions, and finally we set this function, but in some situation we obtained very bad results. So I think that the utility function is crucial here, and we have some ideas how to improve it. And when we will have time, and after A/B test in company, because this PhD study is in cooperation with company. So we could be in accordance with company, not only scientific work, but also business work. So this is our next step to compare few more advanced utility functions.
Yeah. Well, I'm not expert in this area, but as far as I know, recommendation system which are based on graphs, they usually work. There are methods based on edge prediction. So if you want to recommend something, you predict the edge between user and item. So is this approach applicable in your case, and what kind of a performance would you expect?
I don't know what to expect, but this method is definitely, it could be to use. It could be to use, but it's possible to use it here, but we didn't test this. We only would like to generalize RPG beta, because from our earlier works we found that this method RPG beta was superior to other methods used in company. So we had idea to improve. So this maybe this could be improved, this method. So we decided to improve RPG beta, but this what you propose is definitely is usable in this case.
Okay, thank you.
You're welcome.
Thank you, Tomasz. Thank you, Konstantin. There are more questions in chat. So, Tomasz, I think you can answer them even offline in chat or via email.